Swayam Prabha. Digital India. Educated India.
Hello. Today we will start a new topic called proof techniques. Maybe just pen of different colors. This is better. Okay. So we will today study a few general proof paradigms. Later, in later classes, we will look at some specific things like induction, pigeonhole principle, invariance and other stuff. So today, I just mentioned some ways of proving things, and I will explain everything using simple examples. So first, let me start with the concept of direct and indirect proofs. Okay. Suppose you want to prove an assertion P implies Q. Okay. So you assume that P is valid, and along with that you can use results of axioms, definitions, other known facts, and you eventually prove Q. So this is an example of a direct proof. On the other hand, this logical statement is equivalent to not Q implies not P. So you can assume that Q is false, and then we use other known results, theorems, axioms, definitions, blah blah blah, known facts, and we prove that P is also false. You can see that P implies Q and not Q implies not P. They are actually having the same truth table, and therefore they are equivalent. So this is called a direct proof, and this is called an indirect proof, or this is also called proof by contraposition. Okay. So let us see a few examples of such a proof technique. So maybe I start with this theorem or proposition. For all integers n, we have n is odd if and only if 3n plus 5 is even. Okay. So whenever I talk about this P implies Q or something like that, we may often imply that it is something like this: for all x, Px implies Qx. Okay, things like this. So this is one of this form. So for all x, Px implies Qx. This is same as for all x, not Qx implies not Px. So that is proved by contraposition. So let us do this. Proof. Direct proof. First part, actually this is an if and only if statement. So I have two directions. So if n is odd, then I will prove 3n plus 5 is even. So this is, I will make a direct proof. Okay. So n is odd means I can write n as something like 2k plus 1. for some integer k. If that is the case, what is my 3n plus 5? 3 times 2k plus 1 plus 5. And let us do a little bit manipulation. This is 6k. This is 6k. And 3 plus 5, 8. Which is 2 times 3k plus 4. Since k is an integer, 3k plus 4 is an integer, and this is 2 times this. So 3n plus 5 is even. This is a direct proof. And an indirect proof is, I will use for this part, I will use an indirect proof. So what is the direct proof? If 3n plus 5 is even, then n is odd. Instead, I will prove if n is not odd, 3n plus 5 is not even. Okay. So this is an indirect proof. So n is not odd. So what does it imply? N is even. You can have n either odd or even. If it is not odd, it has to be even. So I can write n as 2k. Okay, for some integer k. And then I do the same thing. 3n plus 5 equal to 3 times 2k plus 5, which is 6k plus 5. And I can write it as 2 times 3k plus 2 plus 1. So since k is an integer, 3k plus 2 is an integer. So this is of the form 2 times an integer plus 1. So this is odd, that is not even. Okay. So it's a simple example that illustrates the proof technique called direct versus indirect. Okay. So let us do little bit more. Insert page after. Go there. Good. Then we will do something like existence proofs. So these typically involve proving assertions like this: there exists x such that px happens, or for all x there exists y such that pxy happens. Okay. So these two types of things we often need to prove, and I will give you a simple example right now after explaining this thing in general. So there are actually two ways of proving this. One is called constructive, other is called non-constructive. So for a statement like this, so you actually find a value of x for which px holds. Okay. Now, if you can just show that such an x exists without giving an algorithm for computing this x, this is called a non-constructive proof. On the other hand, if you can actually compute some value of x for which p of x is 2, then this is a constructive proof. Likewise, if I consider this second statement, if I am given an x, if I can find y as an explicit function of x such that p of xy is 2, this is a constructive proof. On the other hand, if I just show that for any given x, there exists some y without specifying an explicit formula of y as a function of x such that this is true, okay, then this is a non-constructive proof. So, Okay, so I will give you a few examples. So, okay, this may be a good example, although I didn't, okay, fine. So, this is the first type. Let me explain. Theorem. There exist irrational numbers x and y such that x power y is rational. Okay, this is of this type, first type. It is not for always there exists certain things such that this is rational. So how do I prove it? Consider this quantity, root 2 power root 2. Okay. I do not know whether this is rational or irrational. Okay. So I consider two cases. So if I call it Z, root 2 is irrational, we know, but I will actually give you a proof. So root 2 is irrational. And now if Z is rational, we are done. Otherwise, Z is irrational, then raise Z to the another power of 2. So this will be 2 power 2 square root 2 power square root 2 square root 2, that is square root 2 whole power 2, which is nothing but 2. So this is rational. Okay. So I do not explicitly say which case happens. Is it, if it is rational, then root 2 power root 2 is rational. So this is one thing. Otherwise, if this is rational, then this power root 2 is 2, which is rational. So this is a kind of non-constructive proof. I cannot explicitly say which case holds, but yeah, either this case is true or this case is true, and in either case we are done. Right. So this is an example of a non-constructive. Okay, this is slightly constructive, but anyway, this is fine. Okay, so I will now look at a couple of assertions of this type. For all x, there exists something like this. Okay. Okay, so this next theorem is something like that. For all positive integers n, there exists a positive integer n, x, let's say, such that x plus 1, x plus 2, up to x plus n minus 1 are all composite. Okay. So that means if I look at the sequence of primes, there are arbitrarily large gaps. I can choose any integer n, and still the sequence of primes will have gap of size n or more. Okay. So here I will produce a constructive proof. This is constructive. So I will explicitly construct an x as a function of n. So I take this as n plus 1 factorial plus 2. So this is an explicit construction. Then what is x? This is definitely divisible by 2. This quantity is larger than all of this 1, 2, 3 up to x, n plus 1. So this is divisible by 2. X plus 1 is n plus 1 factorial plus 3. This is divisible by 3. X plus 2 is n plus 1 factorial plus 4. This is divisible by 4 and so on. Eventually I have x plus n minus 1 equal to n plus 1 factorial plus 2 plus n minus 1, which is n plus 1. This is divisible by n plus 1. Okay. So this example illustrates that we can have constructive existential proof for all values of x. Now I will show another example. This is once again regarding primes, and I will show that we may have non-constructive proofs also. Okay, so this is this statement. For all positive integer n, there exists a prime greater than n. Okay. So this proof is now non-constructive. How do I prove it? So we consider this number n factorial plus 1. This is not divisible by 2, 3, 5 up to all primes less than equal to n, right? So not divisible by any prime, and for that matter any number less than equal to n. But this is a number in itself, so this has some prime factors. So any prime factor of odd divisor, it itself did not be a prime number, but it decomposes into a product of primes, and any prime divisor which may be itself but need not be of n factorial plus 1, therefore must be bigger than n. Okay, so this is a non-constructive proof, because I do not know whether this is prime or not, or I cannot construct prime as an explicit function of n. But we can argue that there exists a prime divisor of any prime divisor of n factorial plus 1 must be greater than n, whatever it is. Okay, good. Okay, then I show another general proof technique. Okay, so this is called proof by cases. So this typically applies to formulas, logical formulas that we want to prove, P1 or P2 or P3, blah blah blah, up to Pk implies Q. If any of these things happen, then Q is true. So how do I proceed? In this case, I have to show all the K implications. P1 implies Q, P2 implies Q, and so on. Pk implies Q. Okay. So now, as an example, consider this theorem or proposition, whatever you call. For all positive integer n greater than 1, I am excluding that case, n equal to 1, 4 to the power n plus n to the power 4 is composite. Okay, so how do I prove it? I will consider two cases. N is a positive integer, it can be either even or odd. So I consider two cases. That is why it is called proof by cases. N is even. That means it is at least 2, 2, 4, 6, 8, something like that. Okay. But then, since n is greater than or equal to 2, you see that 4 power n plus n power 4 is definitely greater than 2 and is a multiple of 2. Right. This gives 2 power 2n. This is, and n is even, so a factor of 2 also comes from n power 4. So it's a number bigger than 2 and it is divisible by 2, therefore it has to be even. And the other case I need to consider is this. N is odd. How will the proof go now? 4 power n plus n power 4. 4 power n is a square, 2 power n whole square. And this one is n square whole square. So if I consider this square, I have to subtract the 2ab term, right? 2 times this times this. So that will be 2 times n plus 1 n square. Now since in this case n is odd, n plus 1 is even. Right? And therefore n plus 1 by 2 is an integer. So this is of the form a square minus b square. So I can write it this way. 2 power n plus n square plus 2 power n plus 1 by 2 n times 2 power n plus n square minus 2 power n plus 1 by 2 times n. Okay. Now it is an easy matter to check that for n greater than or equal to 2, this quantity is positive. I mean this quantity is greater than 1, this quantity is anyway greater than 1. And but for n equal to 1, this will evaluate to 5 and this will evaluate to 1. So for n equal to 1, this is not true, but otherwise for n greater than or equal to 3, this is also a quantity greater than 1, this is a quantity greater than 1, and therefore this quantity is composite. Okay. Good. So this is called proof by cases. Okay. Then you have proof by contradiction. Okay, this proceeds as follows. So, maybe when you consider some statements like this, P can be Q or P implies Q, then I assume that this implication is false. Okay, which means P is true and Q is false. And then use other theorems, blah blah blah, other results, axioms, definitions and all that stuff, and eventually you arrive at a contradiction. Okay, finally arrive at a contradiction. So in this situation something like both R is true and false, like R and not R. Okay. And which implies that our initial assumption that P implies Q is false is not correct. So P implies Q. And this can be, this can also be like simple statements like P. You want to prove P? Not necessarily assuming something. And then you assume P is false. And then arrive at a contradiction like this using a sequence of logics. Okay, so I illustrate this once again by an example, theorem. This is a result we have already used. Root 2 is irrational. This is not exactly something called an implication proof, but it's a statement like this. Okay, so how do I prove? I assume that root 2 is not irrational. That means, assume that root 2 is rational. If that is the case, there exist integers a and b such that I can write root 2 as a over b. Now if I multiply b with both sides such x square, what do I get? 2b square equal to a square. Now, if I consider any number squared, the total number of prime divisors must be even, right? Because if I add something like c equal to p1 power e1, p2 power e2 and so on, pk power ek, c square will be the same thing with the exponents doubled. So the total number of prime divisors for c square is 2e1 plus 2e2 plus ... up to 2ek, which is an even number. Okay. So this side you can see, if I use this result, there is an even number of prime divisors occurring this side. This square also supplies an even number of prime divisors on this side. But 2 is a lone thing. So it says that this number on the one hand has an even number of prime divisors and an odd number of prime divisors. And it is well known this is called the fundamental theorem of arithmetic. The factorization of every number is unique. Therefore, this case cannot happen. We cannot have a number which is equal to this or this having both an even number of prime divisors and an odd number of prime divisors. It is not possible. So it's a situation like this contradiction. Okay, so this side odd, this side even. So a number cannot have both an odd number and an even number of prime divisors. So that's a contradiction, because we are using the standard result which is called the fundamental theorem of arithmetic. That is uniqueness of factorization. Good. Okay, so fine. Maybe I will use another couple of examples. Sometimes we deal with something called cycle of implications. So we give something like 3, 4, 5, some number of statements. If each one of these is true, then all of the other are also true. Okay. So this is called a set of equivalent statements. So I give you an example to illustrate this. For any two integers, or maybe you can say positive. It's not worry too much about negative or integers a and b, the following conditions are equivalent. Okay, I will now state three such things. A is a divisor of B. Two, GCD of A and B is A. And 3, the floor of B by A is equal to B by A. So whenever I make a cycle of implications, what I can typically do, 1 implies 2, 2 implies 3, 3 implies 1. So 3 things I have to prove. Or I can show 1 implies 3, 3 implies 2, 2 implies 1. Okay, so let us proceed this way. 1 implies 2. Why? If A is a divisor of B, this is given by 1, A is a divisor of B. But A is also a divisor of A. Right. So I can conclude that A is a common divisor of A and B. Now if you consider any common divisor of A and B or any divisor of A, it cannot be larger than A, right? No divisor of A, or for that matter common divisor of A and B, can be larger than A itself, but A is already a common divisor, and therefore it follows that A is the greatest common divisor. Of A and B. Okay. So this is one part of the proof. I have to show 2 implies 3 and 3 implies 1. So what does 2 say? 2 says that the assumption is that GCD of A and B is A, right? So A is a common divisor of A and B. In particular, A is a divisor of B. That means I can write B equal to K times A for some integer K. But then B by A is an integer, and if that is an integer, then by the definition of the floor function, B by A equal to B by A equal to K. Okay, so this is proof of the second part. Finally, I have to show 3 implies 1. So it is given that B by A is equal to B by A. So let us call this K. Since floor is an integer valued function, so K is an integer. But then what do I have? B equal to AK for an integer K. So this implies A is a divisor of B. Okay. So this one proofs actually illustrate many, I would say, interesting contexts. Suppose, okay, in proof technique. On the other hand, if I have 4 such things, 1, 2, 3, 4, there are many possibilities. You can prove 1 implies 2, 2 implies 3, 3 implies 4, and eventually 4 implies 1. You can have many other things like 1 implies 3, 3 implies 2, 2 implies 4, 4 implies 1. So 4 proofs you have to make, but you may also do something like this. 1 implies 2, 2 implies 3, 3 implies 1. That establishes the equivalence of 1, 2 and 3. Then you may take 4. So maybe 2 implies 4 and 4 implies 3. Okay. Of course, if you do something like this, you have to make 5 proofs. 1, 2, 3, 4, 5. Whereas here you require 4 such proofs only. But it may so happen in situations where these 5 proofs together are simpler than these 4 proofs. Something like this. Okay, so sometimes also we can do this. So let us see why 1 implies 2, 2 implies 3, 3 implies 4. But here I have proved 3 implies 1. Okay. So I prove that 3 implies 4 also is true, because 3 implies 1, 1 implies 2 and 2 implies 4. So 3 implies 4. And why 4 implies 1? Because 4 implies 3 and 3 implies 1. Okay. Something like that. So such, you say, cycles of implication can be proved easily. Okay. Okay. So we have seen examples of things like P or Q implies R. Okay. Now I want to do something a little different. I want to prove P implies either Q or R. Then what is the logical implication of this? This is equivalent to P or Q or R. Right. This is equivalent to, if I now look at this part, or R, just I put in bracket, not P or Q. This can be written as P and not Q or R. So this is equivalent to, in turn, P and not Q implies R. Okay. So in order to prove that P implies either Q or R, what you can start with is that P is true and Q is false, and then you show that R must be true. Okay. So this is a complete proof. You do not again have to show that P is true and R is false, then Q is true. Only this much is good enough. Okay. So I illustrate this by an example. Maybe I go to another page. So, okay. So here it is, the theorem. Let P be a prime. Okay. Let P be a prime. And A comma B be integers. If P divides the product, that is, it is the divisor of, then P divides either A or B. Okay. Why? So, this is our left side. P divides AB implies P divides A or P divides B. Okay. So, I will assume that P divides AB, but P does not divide A. I have to show that in that case, we must have that P divides B. Okay. So, proof is something like this. So, assume we start with the assumption that P divides AB, P does not divide B. Okay. Sorry. Okay, we can also do this, but anyway, does not divide A, let's say. That's better. P does not divide A. So, it suffices to show that in this case, P must divide B. Okay, so P is a prime and A is not divisible by P. Since P is a prime, the only divisors of P are 1 and P. No other thing. A may have many divisors, but P is not among them because P does not divide A. Therefore, it follows that GCD of A and P must be 1. Okay. So now I will use a result which I will prove later. When we study invariance, I will prove this statement. The GCD can always be written as a linear combination of the arguments QA plus BP for some QV, not positive integers. One of them is usually positive, the other one is usually negative. Otherwise, you cannot have equal to 1 like this. Okay. So, for some UV, set signed integers. Okay. But if I now multiply this equation by B, what do we have? UAB, VPB. But I have assumed that P divides AB, so this term will contribute a factor of P, and anyway I have a P here, so the right side is a multiple of P. Okay, but the right side is equal to the left side, so B must be a multiple of P. So this is divisible by P, and here P anyway resides. So, B is a multiple of P. Okay. Fine, so this is a complete proof. You do not have to prove anything else. Like if P divides AB and P does not divide B, then P divides A. It's not necessary. This is sufficient. Okay. Okay, so these are some, I would say, basic proof techniques. I will consider more sophisticated techniques like induction and other tools in the next lecture. But before stopping today, let me also introduce the concept of these proofs. Okay, so if I, for example, want to disprove a statement like this for all x, px, then it suffices to find out an x for which Px is false. So this is a counter example. Okay. And once again, this construction may be, this proof may be constructive or non-constructive. If we can explicitly construct a value of x for which this is false, you are done. It's a constructive proof. Or if you somehow prove the existence of some x without knowing it explicitly, then it's a non-constructive proof. Okay. On the other hand, if I want to disprove a statement like this, I now need a general proof. Okay, this is false. This means, what is its negation for all x? Sorry. The negation of this is, if this is disproved, then I am essentially proving its negation. And what is this negation? For all x not px. Right. So now there is no question of a counter example. I have to prove this statement for all x. So counter examples do not work here. Okay, otherwise if it is for all x kind of thing, a single counter example is good. So maybe I illustrate this by a simple thing. Actually we have already seen a proof, S7P thing, but anyway let me give you a small example. For all AB in the set of real numbers, A square less than B square implies A less than B. So since this is a for all type of statement, it is sufficient that I can give a simple counter example. So for example, I can take A equal to 2, B equal to minus 3. And definitely A square is less than B square, but A is not less than B. Okay. Okay, so these are all implications of predicate and propositional logic. The set of foundations. These are the set of foundations for all these proof techniques. And yeah, I maybe stop after giving you a puzzle. Okay. So suppose you have, okay, so solve this puzzle and prove it, how you solved it. So this is an exercise. Okay, so suppose you have n bulbs, L1, L2 up to Ln lamps. Okay, so what you do, initially all the lamps are off. Okay. Then in the first iteration you simply switch on all the lamps. Then in the second iteration you look at the lamps number 2, number 4, number 6 or multiples of 2. And if it is on, you switch it off. If it is off, you switch it on. Of course in this case everything is on, so you switch on. Then you look at 3. All multiples of 3. So L3, if it is switched on, switch it off. If it is switched off, switch it on. So toggle the state. And finally you do it for n such steps. So the question is, which of the lamps will be on after this entire process is over. So I will just give you a better way of representing this. So this is the init for I equal to 1, I less than equal to n, plus plus I. Let us say on means 1, off means 0. Okay. Li is 0. So 0 is off, 1 is on. Then you have this loop. And this may be considered as L within square brackets I. Array elements. Then for I equal to 1 to n, plus plus I for j multiples of I, so j equal to I, j less than equal to n, j plus equal to I. So I, 2I, 3I. Only these lambs you just set Lj equal to 1 minus Lj. So if it was off, it now becomes on. If it was on, it now becomes off. So after this, which lambs are on and why? So of course here you have to guess something. Okay, this statement you have to guess, and for why you support by a formal proof. Okay, and you use some simple techniques like what I introduced today. Okay, so I think we have a not so small class already, so I think we can stop. So we will start induction in the next class. Okay, so see you.